In this video, we're going to be describing the motion of an object by using integration. In order to do that, we're going to have to integrate multiple times. So let's make sure we can do that first. So here's an example we can practice with. We're given a function that represents the second derivative. And then we're given two pairs of initial conditions here, an initial condition involving the first derivative and an initial condition involving our original function, or f. So if I integrate or find the antiderivative of this second derivative, I get my first derivative plus our constant of integration. So let's do that first. So finding the antiderivative of this function gives us 4x cubed plus 3x squared minus 4x plus our first constant of integration. Let's go back up to our initial condition where we're told a value on our first derivative graph. So if I input 0, my function value is 4. So if I substitute 0 for x and set my equation equal to 4, I can solve for my constant of integration. So we end up getting 4. So now we can rewrite that first derivative function in its particular solution form, given that initial condition, and we're replacing 4 in that constant of integration spot. So now what we can do is take that first derivative function and find its antiderivative to get to the original function. So if we integrate or find the antiderivative of this function using our power rule, then we get x to the fourth plus x cubed minus 2x squared plus 4x plus our second constant of integration. And we can go back up to our initial condition telling us a point on our original graph or original function graph. If I input 1, my function value is 1. So if I substitute 1 into each of my x's, there should be a 1 right there. Then I can solve for my constant of integration. So substituting and then solving for c, we get -3. So now we can replace that into our function and get that particular solution for the function f. So there's our original function. We can check our work. We could derive this once and make sure we get that first derivative, and then we could derive it again and make sure we get our second derivative. So we're able to check our work here. All right, so let's put that to use. So let's make sure we understand the relationship between position, velocity, and acceleration. If you find the antiderivative of acceleration, you get the velocity function plus a constant of integration. Acceleration can be represented using a of t or v prime of t, recognize both. And then we could find the antiderivative of velocity and get the position function plus our constant of integration. And we could represent velocity two different ways, either v of t or s prime of t. So using that, we'll be able to solve applications involving position, velocity, and acceleration. So in this example, we're given a velocity function, and we're going to be able to find the position at a specific time. So we're given the velocity function. We're given an initial condition involving the position function. And then eventually we're going to solve for the position at t equals 5. So one step at a time, let's find the antiderivative of velocity and get our general solution for position. So using the power rule, we integrate and we find the antiderivative or the indefinite integral here. And we can always check our work, derive that, make sure you get back to the top. We're going to use our initial condition to help us solve for that constant of integration. So if I have an input of 0, my position is 0. So if I substitute 0 into my t-spot and set my position function equal to 0, then we can solve for c. So doing that, we see that c is 0. So then we can rewrite our position function and substitute that for the constant of integration. So we could write plus 0, but it's not necessary. So now we have our position function, and we want to find the position at t equals 5. So I'm just going to substitute 5 or plug 5 into my position function and solve. And so the position at t equals 5 is 75. Let's do one more example. This time we're given the acceleration function, and we're going to be able to find the velocity and the position as we go. So given the acceleration function, given some initial conditions, we're going to be able to use that. So to integrate the acceleration, that's going to give us the velocity plus constant of integration. So if we find the antiderivative of our acceleration function using the power rule, then we get our velocity function with our constant of integration. So let's use this initial condition involving velocity to help us solve for that constant of integration. If I input 0, then my function value is negative 81. So if I input 0 here, well, that's easy enough. We know that our constant of integration has to be what the function equals, so negative 81. So now we can substitute that into our constant of integration spot, and we have our velocity function in its particular solution form given this initial condition. So we can actually find the velocity at a specific time now. We just got to plug 6 into our velocity function and simplify. So we find our velocity at t equals 6 is 27. So now we can take our velocity function right here and find the antiderivative of that to get our position function plus our constant of integration. So find the antiderivative of this velocity function using our power rule, and we get our position function plus our constant of integration. So in order to solve for that second constant of integration, I use my initial condition involving position. So if I input 0, my position is 0. So if I substitute 0 into all of my t spots and set it equal to 0 and solve for c, well, we find that the constant of integration is 0. So when we rewrite our position function in its particular solution form, you could write plus 0 off to the side here, but it's not necessary. So now we have our position function, and we can find the position at t equals 6. So we're plugging t in, or 6 in for t, and simplifying, and we find our position at t equals 6 is negative 54. So there's how we play around with acceleration, velocity, and position using integration.